Welcome to The Explainer. Today, we're going to tackle the core idea that powers pretty much everything you hear about in AI, from self-driving cars to those crazy art generators. And believe it or not, it all begins with a really simple puzzle.
So, let's just jump right in with a big question. For a long time, the simplest computer models tried to understand the world with just one basic tool, a single straight line. But is that really enough?
Well, for a simple problem, yeah, for sure, it works perfectly. If you're trying to find a pattern like the bigger the house, the higher the price, all your data points are going to line up pretty neatly. You can just draw one straight line right through them. That's basically what linear regression does, and bam, you've got a solid answer.
But let's be real, the world is rarely that simple, right? So what happens when things get messy? Just imagine trying to separate a bunch of red dots that are completely surrounded by blue dots. How are you going to do that with one straight line? You can't. It's just impossible. And this is where those classic, simple models just completely hit a brick wall.
And this brings us right to what we can call the straight line problem. And it's a big deal. This was the fundamental challenge, the major headache for AI researchers for a long time. I mean, how do you teach a machine to see in curves when the only tool you've given it is a ruler?
Now, there's a technical term for this, of course. It's called underfitting. And here's a great way to think about it. It's like trying to perform delicate surgery with a sledgehammer. The tool, your model, is just way too simple, too blunt to grasp the complex, curvy reality of the data. It tries, but it just can't capture the real pattern.
Okay, so if one straight line isn't going to cut it, then what's the answer? What do we do? Well, this is where we get to the aha moment, a really clever idea that, honestly, changed everything.
The big breakthrough was a total shift in mindset. People stopped trying to build one single, heroic model to solve the whole problem. Instead, they started asking a different question. What if we used a team? What if we combine a bunch of these simple models and have them work together?
Picture this. You have a few of these simple models, right? Let's say Model A draws a line on the left side of our dots. Model B draws one across the top, and Model C draws one along the bottom. Now, individually, none of them solve the puzzle, not even close. But then you bring in a manager model. Its job is to look at all those simple lines and combine their answers in a smart way. And suddenly, together, they can form a box, or even something kind of like a circle, perfectly fencing in those dots.
And that right there, that is the core idea behind a multi-layer perception, or MLP. This is like the ground floor of deep learning. It's all about stacking these simple models, these simple line drawers, in layers, so they can team up and solve problems that are way too tough for any one of them to handle alone.
All right, so this team of models idea sounds great, but how does it actually work? To really get it, we need to peek under the hood, you know? Let's look at the toolkit, the basic building blocks that make up this team.
The smallest piece, the most fundamental unit. You can think of it as a single player on the team. It's called a perceptron, but pretty much everyone just calls it a neuron. And all it is really is a tiny little machine that makes a decision. It takes in some numbers, does a super quick calculation, and spits out an answer.
Here's a fantastic way to think about it. Imagine each neuron is just one voter in a huge election. It looks at the evidence coming in, that's the data, and it casts a simple vote, yes or no, cat or not a cat. Super simple. And these voters aren't just a random mob. They're organized into neat rows called layers. You've got the input layer. That's just the front door where all the raw data comes pouring in. Then you have the hidden layers, and this is where the magic happens. This is where the team actually does its thinking, finding all the interesting patterns. And then at the very end, you get the output layer, which gives you the final answer, the final verdict from everyone. Okay, so if you have all these voters, how does the network know which ones have good opinions, which ones should it listen to more? The answer is something called weights. A weight is just a number that basically tells the network how important a connection is. It's like turning up the volume on the smart voters and turning it down on the ones that aren't helping.
It makes total sense when you think about it. If you're predicting a house price, what's important? Square footage, right? So that input gets a really high weight. But the color of the front door? Probably not so much. So it gets a really low weight, close to 0. And learning, the whole process of training a neural network, is really just about the network figuring out how to tweak all these weights to get them just right.
Next piece of the puzzle is something called the bias. A good way to think of it is like a little thumb on the scale for each neuron. It's this extra number that gives the neuron a starting point, a baseline tendency to say yes or no, even before it looks at any of the inputs.
And here's a killer analogy to make it stick. Think of a salesperson.
Their commission, that's like the inputs multiplied by the weights. But they also get a base salary, right? A fixed amount no matter how much they sell. That base salary is the bias. It just makes sure the neuron has a chance to be active even if all the inputs happen to be 0.
Okay, we've got our neurons, our weights, our biases, but now we get to the secret sauce. This is the single most important piece of the entire puzzle. This is what turns the whole thing from just a fancy calculator into something that can actually learn.
And I'm not kidding, you gotta lean in for this part. Because without this one simple idea, our whole team of models thing, it completely falls apart. All those layers, all those neurons, they would just collapse back down and become one single, boring, straight line again. All that work for nothing.
So what is this magical piece? It's called the activation function. And the easiest way to think of it is just as an on-off switch for each neuron. After the neuron does its math and adds everything up, the activation function looks at the result and makes a simple choice. Is this signal important enough to pass on? Should I fire, or should I just stay quiet?
And the difference this makes is, well, it's night and day. Without these activation functions, a network is just doing a bunch of simple line math. And when you add a straight line to another straight line, you just get another straight line. It's boring. But by adding this simple on-off switch, you give the network the power to create curves and bends. It can finally combine all those simple lines to draw basically any complex shape it wants.
And just like that, problem solved. We've cracked the straight line problem by putting together this team of simple neurons and giving each one of them that crucial on-off switch, the activation function. We've finally given them the ability to work together and draw that complex shape we needed to separate our dots.
So that really brings us to the final big idea here. We started with this super simple puzzle, right? Just separating some dots. But the solution we found, this idea of stacking up simple models with on-off switches, is so much bigger. I mean, think about it. If a team of simple lines can teach itself to draw a circle, what else can it learn? What are the limits? What other incredibly complex patterns out there, in language, in science, in art, can they learn to see?